吗？13个小时吗？行啊，那也行。那这样我就过去吧，我就过去在边上站着，你稍微支持一下，也不说。
Well, I wanted to talk to Wentao for a minute. I don't know if Wentao was listening to that talk by Yongshao Horn, but I hope so.
Yeah, that electrolyte looks interesting.
It does. I'm not sure we know exactly what it is. Have to go and look back at the PowerPoint.
Jeff, do you have a PowerPoint?
What's that?
Do you have Yongshao Horn's PowerPoint?
I think it's possible to get it by going to the Stanford X website. They recorded it, that's for sure. Okay, so I guess I need to get started here. Okay, let me share my screen here. Okay, can people see my screen and hear my voice?
Yes.
Okay, well, good morning or good afternoon, whatever it is. So I want to talk today about graphites and negative electrode materials. So the idea is you have a positive electrode material, which is somewhere down here on the lithium binding energy scale. So NMC or NCA, lithium nickel oxide, lithium cobalt oxide, they're all down here. And what you want for a high voltage lithium ion cell is a negative that's very different in its binding energy for lithium inside the material. So graphite is, of course, right way up here, which gives you the biggest voltage difference, and you can make a 4-volt cell roughly. Okay, but there's another carbonaceous material listed in this chart called coke. Now, what is it? And there's all these other choices that you could pick as well, like tungsten dioxide and molybdenum dioxide, and you know, they just don't give cells with high energy density, and they use expensive transition metals, so you don't want to use them. So we're going to focus here on things that have value in lithium-ion cells. So this particular lecture will cover graphite, what is called soft carbons and hard carbons, talk about how to make them. It'll talk about lithium titanate, which is used as a negative electrode. And we'll talk about alloys later, which means lithium going into silicon or tin or silicon oxide later in the course. So this is basically conventional negative electrodes for lithium-ion cells, which are interesting in their own right. So this is the structure of graphite viewed from the side. It's called 2H graphite. It has a 2-layer unit cell, and it has AB-AB stacking. And I want to draw on my document camera what's being talked about here, because it's a little bit different than hexagonal close packed layers. So I'm going to go to my document camera. So I believe I've stopped sharing, and I believe you can see my document camera. Is that correct?
Yes.
Yes.
Okay, great. So let's draw a plane of carbon atoms in graphite. All right. So they look something like this. And everybody likes to draw these, oops, that should have been there. Everybody likes to draw these honeycombs, indicating where the carbon atoms are. Okay, so I won't draw too many just because it takes too long, right? But I think you can see that. So the question is, where do you put the next layer that you stack on top of this? And you have, again, like in the hexagonal close packed layers, there's two choices for the positions of the next layer. So let's say we put the next layer, we start with a carbon atom here. I'll make it in black, make it a big circle. Then the hexagonal honeycombs would line up like this. Whoops. Yes, I guess that's right. So maybe I'll put squares at the corners of those atoms. So what happens is you have a carbon atom that's centered over the empty hole of a hexagon shown here, right? Now I could have picked the position differently, and for some reason I can't find my red pen. So I'll try using a pencil. I could have picked this position instead. Let me think a minute here. Yeah, I want to pick this position. So take a triangle there, like that. And then I would be like this. Can you see the pencil, by the way?
Yes.
Yeah.
Okay. Okay, so the pencil lines, the black lines, and the blue lines are not coincident. So the blue we would call the A position. The black we would call the B position. And the pencil we would call the C position. And when graphite has different stacking sequences. So we'll go back to the PowerPoint. The most common form of graphite is stacked A, B, A, B. So it goes a blue layer, then a black layer, then a blue layer, then a black layer. Okay, so I'll share my PowerPoint again. Where is it? I guess it's here. Make it full screen. Yeah, so this is AB stacking. It's called 2H because it's a 2-layer unit cell. You go from A to B and back to A again, so you have expand the unit cell, and it's called 2H. There's another less common form of graphite called 3R. This is found as a component in natural graphite. It's rare to see a lot of it in artificial graphite, and we'll talk about the difference between artificial and natural graphite coming up. But in this form of graphite, the stacking is ABC, ABC, ABC. So that means it has a 3-layer high unit cell. All right. When lithium is fully intercalated into graphite, it forms lithium C6. This is sort of a side view, so it's really hard to see where the lithium atoms are. If we look down from the top, this is what we see, okay? We see the lithium atoms in these centers of the honeycombs. Now remember, the graphite started as ABAB if it was 2H. But now all these honeycombs are right on top of each other. So when the lithium intercalates, it goes to AAAA stacking. The graphite sheets are in AAA stacking. So there's sliding that happens. When the graphite is empty, it's AB, AB, AB. And when the lithium is in there, it's AAAA. So, can you see me at this time?
Yes.
My hands? All right.
Yep.
So here we are. I have 2 graphite sheets in AB stacking. They're slightly shifted. And then the lithium goes in and they become lined up. And then the lithium goes out and they shift again. So every time you charge and discharge the lithium ion cell, this is happening. Every time, every time, every time. And you can do this for tens of thousands of cycles. That should blow your mind. If it doesn't, you may not have a flowing blood. Blood may not be flowing.
Hi, Jeff.
I went out.
Does this apply to both the natural graphite and the artificial graphite, the 2 types of the graphite, AB, AB, and ABC, ABC?
Natural graphite is mostly AB, AB, but sometimes in natural graphite you will find small component of ABC, ABC. Artificial graphite is almost always primarily AB, AB.
Okay, thank you.
All right. Anyway, I hope that astounds you that this can happen. You know, it's really incredible.
Hey, Jeff.
Yeah.
Is that why we see volume expansion upon when lithium is intercalated due to these changing in stacking?
In part. Let me go back a slide. Can you see my screen again, my PowerPoint again? I don't remember if I put it on.
We can.
Okay, so the spacing between graphite sheets with the lithium in is 3.7 angstroms in between the sheets, okay? Here, a 2-layer cell has a spacing of 6.7. So the graphite distance, the layer distance is 3.35. So the layers move apart from 3.35 to 3.7 when the lithium goes in. Part of it comes about from this, you know, change in stacking, but a good fraction of it just comes from the physical size of the lithium that's in there.
Okay, got it. Thanks.
So for whatever it's worth, I'll just show you some of these structures in Vesta and turn them around so you can see things a little better. I'm never sure how to do this. I guess I have to stop share and then try to share again and find Vesta. Here we go. Okay, can you see my screen? Can you see this crystal rotating? Okay, so this is 2H graphite with the ABAB stacking. When you look down from the top, so you don't see any empty honeycombs the whole way through, right? So when we look at 3R graphite from the top, it's going to look different. So we're going to do that now. This is 3R graphite, and we're going to look from the top now. Where is the top? You said wondering. Where am I? What's happening here? It's ABC, ABC, right? Okay, here we are from the top. So now you can see that you've got carbon atoms on each of the A, B, and C sites corresponding to what I drew on my piece of paper. And then if you look at the lithium C6 and you look from the top, oh, what is this? That's not even real. This is garbage. Let me get rid of this. Ignore this. You've never seen this. Okay, this is lithium C6 here. And you look from the top, you see the empty honeycombs for the AA stacking, and you see the lithium atoms in not near neighbor sites, but next near neighbor sites. And we talked about the fact that this is the limit. You can't put them in near neighbor sites, and this is because when the lithium goes into the graphite, it tends to transfer charge to the graphite sheets. So it's sitting in here, if you like to think of it as an ion. And then when you put two lithium ions so close together, the Coulomb repulsion is very, very large. And it just takes too much energy to put them close together. And what you learn is the lithium would rather electroplate on the surface as compared to filling near neighbor sites. It's just more energetically favorable to plate lithium on the surface compared to fill near neighbor sites because of the large Coulomb repulsion that's present. Okay, so I'll go back to my PowerPoint again. Oh my. Okay, that's gone. We get the PowerPoint back. PowerPoint's disappeared. I don't understand what happens here. Has my PowerPoint appeared for you?
No.
Where did it go? Okay, here it is. It's really bizarre. All right, so here's the PowerPoint. I think you can see it, right?
Yep.
Okay. So now we're going to talk about the graphite voltage curve. When lithium is intercalated into graphite, what happens? Okay. So you start with empty graphite over here on the left. And as you add lithium, the first thing that happens is a tiny amount of lithium goes in between every set of layers. And maybe the layers stay in AB stacking. I'm not sure that that's known. So what you see in the voltage composition curve in that part is a voltage that comes down from about 0.8 volts to about 0.2 volts, just before 0.2 volts, a very steeply varying voltage curve. And that phase is called 1 prime. What 1 prime means is every layer, every interlayer space has lithium, every one. That's called stage 1. And the prime is there because every layer has just a tiny amount of lithium in it. You go over here to the very far right, when you have 1 lithium per 6 carbon, that's the structure I showed you in Vesta, LiC6, and that's called stage 1. Then what happens? Well, then there's this funny little plateau here where the material exists in two phases. One of them is stage 1 prime and the other is stage 4. What is stage 4? It means that I don't have stage 4 shown on the diagram, but I'll explain what a staged phase is. Stage 3 is there's a full lithium layer between two carbon sheets, then two empty ones, and then a full one, and then two empty ones. So every third interlayer space is full of lithium. That would be stage 3. So stage 4 would be every fourth interlayer space would be full of lithium. So these interlayer spaces are called galleries in the jargon. So stage 4 has every fourth gallery full of lithium. Okay, so where my mouse is right now in the discharge curve, you would have stage 4. Then the voltage drops relatively steeply. And at this point where my mouse is right there, near the L and 2L, you would have stage 3. So stage 3 looks like this. And then you go along a little bit more and it goes to something called 2L. So stage 2L is stage 2, but every layer is only about half as full of lithium as it could be. All right, so each gallery can hold 1 lithium for 6 carbon, but in stage 2L, there would be about 1 lithium for 12 carbons in this gallery. When you go across this flat spot, those interlayer spaces fill up. And when you get over here, every gallery, every second gallery is full to the max, okay? Every second gallery is full to the max at this point. And then as you go across this plateau, you make a transformation from stage 2 to stage 1.
Hey, Jeff.
Yeah.
So when you go from stage 3 to stage 2L, stage 2L is actually less filled up than stage 3, right?
No, the stage 3 is not completely full in the lithium layers either.
Okay.
The galleries aren't completely full. If it were full, the stage 3 would be at 1/3 on this scale. So it's about half full as well.
Got it.
Yeah.
And then second question is, when you showed on Vesta how the lithium ions are filled, wouldn't you expect that from one adjacent gallery to another, the lithium are filled in different sites because of the repulsive force between the lithium ions?
Yes, that can be the case. It can be the case that the lithiums are not directly above each other.
Okay.
Yeah.
Thank you.
Now there's something that's really interesting, which is how do you go from stage 3 to stage 2? Because you add a little bit more lithium just across this tiny little plateau right here, this little bump. It's stage 3 here and it's stage 2 there. But you see, this is completely empty, and now it's completely full. And this was completely full, and now it's completely empty. Like, did all the lithium just completely move out of those layers? Okay, so I forgot to tell you that the lithium cannot move through a carbon sheet. People have done experiments. It just does not go across a carbon sheet. It can't fit through those honeycombs. So what the heck happens? And this was a huge confusion long ago. And I'll show you what happens. I'll go to my document camera. Okay, so I think you should see my document camera now. Is that correct?
Yep.
Okay. So I'll try to draw this. It's been a while since I've drawn this. I may screw it up. So the thing is, I'm going to start again, because I have to make 2 drawings, not just 1. All right. This is what stage 3 is thought to look like. These islands of lithium are micron size. But every gallery has the same amount of lithium in it. Oh, what am I doing? I've messed this up again. Jesus. I'll start again. Sorry. I love online teaching. Okay, let me get this right this time. Here we go. This is going to work. So we have lithium here, and we have lithium here, and we have no lithium here, no lithium here, and we have lithium over here. And then we go back to the beginning, which looks like this. And then we go like this. All right. So this is stage 3. Every layer has got the same amount of lithium in it, but there are these islands about 1 micrometer in size. And why do they form? Well, once you have 1 lithium atom that expands the layers, it's easier to put the next ones nearby. So there's an attractive interaction between the lithium atoms within a layer. But, like Eric mentioned, there's a repulsive interactions between lithium atoms that are above one another. So these islands try to separate from one another. So the thing is, stage 3, every layer has the same amount of lithium in it. So to go to stage 2, all you have to do is do this. So that lithium redistributes itself as you add more. And as you add more to this one, that redistributes itself. Because you're just adding more, and this island gets bigger, and then the next one goes like this. So this is called the island model of staging, because they have these islands. And it explains how you can go from stage 3 to stage 2 without having all the lithium ions go out of the crystal and go back in again. And this was figured out in the 50s by Domas and Herold. And it's called the Domas-Herold Island Model of Staging. I see Wen Tao has his hand up. I don't know if it's for real or if it's fake. Do you have a question, Wen Tao?
So that was the previous one. That was the previous
Okay,
question. So.
Cool. Okay, are there any questions about this island model of staging stuff?
So just oh, sorry, go ahead.
Oh, I was just going to refer back to the other model where you didn't have the stages like kind of bending there. I think that's called the Rudolph model. So did it just kind of dance around the transition from stage 3 to 2?
I don't know what dance around means.
Like how did it explain it before the Doma-Herald model?
There was no explanation before the Domas-Herald model. It was a big question. You know, and this was verified by looking carefully with, you know, with microscopy to learn where the lithium or the other intercalants were. It's a lot easier to tell with a heavy atom intercalant than with lithium.
Okay.
Okay,
So-
so let's.
All this model is saying basically is that you form islands of lithiated graphite that get bigger and bigger as you add more lithium, and that's how you get the different stages. That's basically all this is saying, right?
That's basically what it's saying, and it's saying that lithium atoms within the layer attract one another, and from layer to layer they repel one another, so that you tend to form these islands that don't want to sit on top of each other. Okay, so let's go on here. So I'll share my PowerPoint again. Lo and behold, it appears for once. All right, so let's go on. Right. So this is really very cool. So this is some work that Alex Luley did a few years ago in our lab. So he put a cell into this rigid frame with a pressure sensor, and then as the cell charges, you can see the fractional volume change, which is excuse me, you measure the pressure, okay? And what Alex is plotting here is based on crystallographic measurements of lithium intercalated graphite. What should the fractional volume change of the graphite be as you add lithium to it? So this is no lithium over here, and this is full lithium C6 at the right side. So as you go through the stage 1' area, and then to stage 4 and stage 3, and then eventually you get to stage 2L over here. From stage 2L to stage 2, you're just filling up islands. Okay, you're not making stage 1. So the volume of the graphite remains constant as you go from stage 2L to stage 2. You're just increasing the density of lithium within those islands. And once you have a few lithium between the adjacent carbon layers, it props them open so that you can add more and not cause them to expand more. And then when you go from stage 2 to stage 1, there's this big volume increase. Remember, a layer with lithium between, the spacing between those two carbon sheets is 3.7 angstroms, and with no lithium in between is 3.35. So you expect a 10% change in the volume just because of the fact that the layers move apart. But there's this region that's absolutely flat, okay? And the other electrode in this cell was NCA, which across this portion of the state of charge of the cell has very little volume change as well. So what does the pressure sensor reading look like? Well, this is what it looks like, okay? So this is the pressure, and this is the voltage of the graphite at the same time. So like I told you, you're in the 1' phase, then you go from 1' to 4, come down to 3, and this plateau is the stage 2 to stage 2L plateau. And here, the pressure of the pressure sensor doesn't increase at all because the thickness of the pouch cell doesn't change, okay? So this is incredible that a macro measurement can probe these atomic scale changes. It's really, when you think about it, it's again, if you have any blood flow at all, this should really impress you. It's crazy, in fact. Okay, so then you go off the stage 2 plateau and onto the stage 2 to stage 1 here. And that's where the volume of the graphite starts to increase linearly. And sure enough, up it goes, right? The pouch cell swells, it tries to swell, but it presses against the pressure sensor, increases the pressure. And it's completely reversible, right? It goes back when you remove the lithium from the cell, it goes back exactly how it was. For me, when we did this, like this is one of these eureka moments you have 4 or 5 times a year as a scientist, and you know, you're just adrenaline rush and you have chills in your spine and you're going crazy. So that's how you know you have blood flow. So if you want to know the specific capacity that graphite can have, it's really very simple to do these calculations. You can add 1/6 of a mole of lithium for every mole of carbon, because the limit is LiC6. Faraday's number is 96,500 coulombs per mole. You want to know how many milliamp hours you have per gram. So you figure out 1/6 of a mole for 1 carbon, how many coulombs per mole. There's 12 grams of carbon per mole. And it turns out there's a conversion factor, 3.6 coulombs for every milliamp hour. So if you multiply these things out, you get 372 milliamp hours per gram. And that's a number that is the theoretical specific capacity of graphite. So I guess back in about 1987, when we started working on carbons as negative electrodes for lithium ion cells at Moly Energy, you know, there's thousands of commercially available carbons: petroleum coke, carbon fiber, buckyballs, carbon nanotubes, carbon black diamond, activated carbon. You can make artificial graphite from tar, from coal pitch, from petroleum pitch, from needle coke, all kinds of stuff. So, you know, in those days, the question was, you know, what is in fact the best? Are any of these better than graphite? So there's a paper that we published in Science in 1995, which shows the specific capacity in milliamp hours per gram as a function of heat treatment temperature for a variety of carbon samples. Okay, so you take different organic precursors and you heat them to different temperatures under inert gas. This is called pyrolysis or carbonization. If you heat them under air, they just burn, you know, carbon burns. That's how you heat a house with coal. So you have to heat them under inert gas, nitrogen typically, all right? So if you start with one set of precursors and you heat to 500 degrees C, lo and behold, you get this massive specific capacity, 800 or 900 milliamp hours per gram. Why aren't these used in lithium ion cells if they're so enormously huge capacity? And then this in the region 3 here, this is where if you take what's called a hard carbon precursor, which is things like wood, say oak or maple, or sugar works well, and you heat to this temperature range around 1,000 degrees C, you get 600 milliamp hours per gram. This set of soft carbon precursors, if you continue heating them, the specific capacity goes way down, below 200 milliamp hours per gram. But then eventually, when the heating temperature gets really large, you start to get near this 372 milliamp hours per gram. This is artificial graphite here. Artificial graphite is made at temperatures like 3,000 degrees centigrade. And just to put you on the scale, that's half the surface temperature of the sun, you know. And if you have any blood flow, you should be thinking, Are you kidding me? 3,000 degrees centigrade? That's pretty darn hot. And in fact, think about how you would make a furnace to hold something at 3,000 degrees C. There's only about one thing that doesn't melt at that temperature, and it's graphite and diamond, okay? Those are about the only things that you could ever build a furnace out of to hold, to do this work, to do this heat treatment. So it's pretty interesting to think about how these things are made. Anyway, I want to tell you about these particular regions, okay? And I'm going to start with this region 1, which is traditional intercalation and graphite, like we've been talking about. Any questions about this? I hope some of you are thinking, why aren't we using these carbons in regions 2 and 3 in lithium-ion cells? I hope. Okay, so this is what the voltage curves look like. Okay, so we talked about the graphite voltage curve, 372 milliamp hours per gram, and all these bumps and wiggles due to the presence of these transitions between the stage phases. So a carbon in region 2, and it says here is petroleum pitch heated to 550 degrees C. You know, look at the big capacity, 900 milliamp hours per gram, but there's this big hysteresis loop. You put the lithium in, the voltage is low, and you take it out, the voltage is around 1 volt. Whereas with graphite, there's no hysteresis at all. Perfectly reversible. And then in region 3, things look pretty interesting. There's a sloping region and then a plateau. And the plateau has no steps and wiggles in it like graphite does. It's just sort of a smooth, straight, sloping curve, and then it comes back. And this is pretty reversible without much hysteresis. So big differences here. So there's a lot of mysteries here. What's this hysteresis loop? Why does this have two different behaviors, a sloping region and a flat region? What the heck is going on here? And none of these questions were answered in 1990. And, you know, we sort of took it on ourselves to figure this out because it was important for the lithium-ion business to understand what you could and could not do. So I had a bunch of graduate students who did a lot of work on this. Hang Shi and Tao Zhang in particular did most of the heavy lifting in this stuff. Tao Zhang, by the way, at this point has a net worth of 200 million US dollars because he has made a very successful carbon nanotube company. Okay, so to understand all of this, we have to understand how carbons and graphites are normally made. And like I say, most commonly you pyrolyze an organic compound in an inert atmosphere. So what is an organic compound that might be used? And you have to use an inert atmosphere because otherwise a carbon will burn up. Organic compounds that might be used can be anything, and I'm not joking. Coconut shells, rice husks, straw, wood, tar, coal, anything. People have tried them all to see what you get, not just for battery applications, but for gas filtration, water purification, all kinds of things, all right? And the real question is, what happens during pyrolysis? So this talks about what happens to crude oil when you pump it out of the ground, you know, and then you want to use it to make gasoline and other petroleum products. What do? You put it into a giant distillation tower and you heat it and the vapors go up. And the products with the lowest boiling point go highest in the still. You know, so things like gasoline and kerosene come off near the top, and materials that are used for rubber and plastics and paints come off near the middle, and fuel oil comes off down at the bottom where it's relatively hot. But at the bottom, things that at these temperatures don't really evaporate much in the still, like asphalt and tar, they come out the bottom, okay? And these asphalts and tars are used to make artificial graphite. And we're going to talk about artificial graphite made from petroleum pitch or asphalt type stuff. So that tar, that asphalt, is comprised of a lot of aromatic hydrocarbons. And as you heat them to the temperature range around 300 to 500 degrees C, what happens is aromatic rings start fusing, and there's loss of hydrogen as more and more of these rings join together. So this molecule here, it has hydrogens not shown at every vertex here. There's a hydrogen atom not shown. So this one would have, you'd have to count the exposed vertexes. It looks like 10 hydrogens for 3 rings. And as you heat more, you get more hydrogen loss and more rings join together. So you would have less hydrogen per carbon in this bigger molecule. So the hydrogen to carbon ratio in a material, in a carbon that's being pyrolyzed, the hydrogen carbon ratio gives you a good indication of how many fused rings you've got, right? So here the hydrogen carbon ratio is 10, and then how many carbons are there? I think there's whatever there are. It's about a hydrogen carbon ratio of about 1. But here the hydrogen carbon ratio is less than 1. And then as you heat treat more, these planar rings of carbon hexagons get bigger, and you've lost more hydrogen as well, okay? And then with further heating, you eventually get into the graphite structure, all right? But I have to talk about what happens in this temperature range that's not shown on this slide, okay? Because it's really incredibly important. So I'm going to go to my document camera for that, okay? Timing's very good. We'll just get through this part and then we'll stop. Okay. I think you can see my document camera. Is it true?
Still a PowerPoint right now.
Oh, okay. How about now?
There you go. Thank you.
All right, so you should be able to see 2 pieces of paper. One that has the cross hatching of a typical quad ruled piece of paper, and the other one should be white. Do you see those 2 pieces of paper?
Yep.
Okay. So imagine that we've heated the petroleum coke to around 1,000 degrees. At that point, we have sheets of those carbon honeycombs with a bit of hydrogen around the edge, and they're not too big. I don't know, they might be 50 nanometers across. And they're big enough so that they want to be parallel to one another. You know, if they're like this, that's not very energetically favorable. The thing is, they're randomly rotated relative to one another at this temperature. Okay, so they're parallel, but they're randomly rotated. And this random rotation is called turbostratic misalignment. And what happens as you heat the graphite more and more is the lateral extent of these sheets keeps growing. And then it gets less and less probable for them to be in this random alignment. They don't like it. They can minimize their energy by locking in to the AB stacking. So this would be A, and then the white one would be B, and then you go back to the cross and back to the white, AB stacking. Okay. So turbostratic misalignment turns out to be incredibly important in understanding the behavior of graphites and how they intercalate lithium. So I'm going to go back to the PowerPoint. So at about 1,000 degrees, the probability for turbostratic misalignment between adjacent layers is 1. All adjacent layers are randomly rotated with respect to one another. In natural graphite, which has had the advantage of high pressure, sitting in the ground for millions of years, the probability of turbostratic misalignment is about 3%. So in between 3% of adjacent pairs, you'll find a random rotation. And then it goes AB, AB, AB. And then at some point again, you'll find a random rotation with about a 3% probability. Artificial graphite made at 3,000 degrees C would have a probability P for turbostratic misalignment of about 9%, 8%, maybe 7%. Okay. And if you had perfect graphite, the probability for turbostratic misalignment would be 0. Okay, any questions about that?
Hi, Jeff.
Yeah.
Does this p-value affect the performance of the lithium cells?
Oh yes, it's absolutely critical. So we're going to talk about how that is important in the next lecture, which will be on Monday.
Okay, thank you.
So if you won't be able to sleep at night, you could read ahead in the PowerPoint. If you're willing to wait, I'll cover that on Monday.
Okay, thanks.
Hey Jeff, are we going to discuss of why hard carbons are not fully graphitizable?
We are definitely going to discuss why hard carbons are not fully graphitizable.
Okay.
Yeah, we'll come to that maybe Wednesday or maybe Monday. I don't know how long it will take. Hard carbons are really cool. And I'll explain the difference between soft and hard and why it takes place. All right, everyone. So I hope that this was useful, and I'll see you on Monday.
Thanks, Jeff.
Goodbye. I think Saad will send me the recording and I'll pass it on. Okay, bye.